Hey there. So, guess who's back with more calculus? Today we're going to talk about a new unit in maximums and minimums and what those are. So we're going to step away from derivatives for just a second until they start to tie back into this. But we're still going to be looking at graphs and curves on, well, curves on a graph. So, say we have a graph, looks like this. This is our x-axis, this is our y-axis, and we have a curve that looks something like this. Pretend that it doesn't go back in. Um, Actually, I just need to erase that. Goes like this. Okay, so you can see that it has peaks and it has troughs. It has places where it's really high, places where it's really low, and everything in between. Now, there's two terms that we're going to be discussing. Uh, well, technically four if you want to get all the combinations, but those are maximums and minimums. Maximum and minimums are points on the graph where our function is at a low point, or cut this off, or it's at a high point. There are two types of these. So there are absolutes and there are locals. An absolute variable or absolute maximum or minimum is the point on the graph at which you have the very highest or the very lowest value. So the very highest on this one is obviously at the top of this peak. I'll just mark it right there. This is our absolute maximum. And our absolute minimum, let me just be clear, I'll remove that so it's a bit more obvious. Our absolute minimum is going to be right here because this is the lowest point on the graph. I can go to the side and there's no other point on the graph that will go below it. So absolute minimum. Boom. So that's pretty simple. You just have to identify the highest and the lowest point on your graph. Now, there is an exception. Let's say that you have a graph that goes not just to an endpoint. You see, this one is defined, like it's from -1 to wherever this value goes, and it stops. However, let's say you have a function like x cubed, I don't know, that goes down to infinity. So limit as x approaches infinity, y is going to approach, in this side, negative infinity. There is no absolute minimum at this point. So absolute min does not exist. So why is this? So it gets into the theory of what the maximum and the minimum is. So you can think about it like a limit. So if the limit of that number approaches a specific value from both sides, it has to be a fully defined limit, and that point is bigger than the others, or all others in your function, it is going to be an absolute maximum or an absolute minimum. And here, if something is approaching infinity, that's not really a very valid limit. We want a real number. So it doesn't work. Same goes for if you have an undefined whole at the end. So we go, and then it gets to here, but this point, the last x value, is a whole. That doesn't work either. So it stops. Partially because the limit isn't defined from this side, and partially because it doesn't actually reach a value. So that's what an absolute minimum and an absolute maximum are. Now, let's move on to what a local minimum and a local maximum are. So, an absolute covers the entire function, including the endpoints. So, an endpoint, if it's defined on a certain domain, will be the maximum and the minimum, if it is. A local is just within a certain range. So, it with right here we have a minimum. So as we approach this point right here, let's say it's a limit from the right and the left, or whatever x value this is, x right here, this is lower than all the points in its vicinity. Like if I chose right here, still lower. If I chose right here, it's lower than that one. As it comes here, it zeroes out. it flattens out, and then it turns around. Same if you go to the maximums, like let's look right here. Between this point and this one, this is the maximum. It doesn't get higher than that within the vicinity. Everything else starts getting lower. And of course right here, this one is also a minimum. So those are local minimums and local maximums. You will only ever have at max one absolute minimum, one absolute maximum, but you can have infinitely many local minimums, maximums. If I'm not wrong, this is just me trying to remember. The limit on that is not actually infinite; it's 28 for some reason, but that's what it is. Anyways, that's irrelevant for what we're talking about right now. But that's what an absolute maximum and absolute minimum are. Uh, and until we start talking about how derivatives factor into this, which isn't very hard either, we're just going to talk about some exceptions so you don't get confused when you're given some weird examples. So let's say we have an absolute value function that goes like this. So at this point, right here on the bottom, the limit does not exist. There is no derivative here. But, and that's because sharp corner, but it is an absolute minimum and a local minimum for that matter. So just keep that in mind that if you have a sharp edge or corner, and it can even go in like a zigzag, these are going to be maximums and minimums. You don't have to worry about that. That'll be important when you start using derivatives with this. Let's see what else there is. Okay, holes. So let's say we have a curve, and there is a hole on the max or the minimum. So let's say right here that we have a hole. So this would be a maximum or a minimum, but it's not actually defined. So, you know what it is? It's not a maximum or a minimum. Even though it is a limit as it approaches that point, it's not defined on the original function, so it can't be a maximum or minimum. Now, I'm going to double check something. Okay, I confirmed it. So we have the hole. This isn't a maximum or a minimum because that point is not defined. That's the real reason. But if I define the point somewhere else, like right here, so at x1 comma 20, let's say this has a y value of 20, then this is an absolute maximum because it's at this part. It's defined and it's got it on both sides, therefore it is a minimum, or maximum in this case, because it's higher than everything around it. So even though it's a hole, it is still a minimum slash maximum, depending on the case. And yeah, so I went over everything else. One other concept, which is incredibly simple, it's going to make you smack your forehead and be like, my 5-year-old could have told me that, is that if you have a actually, let me remind myself what it is. It's called Fermat's theorem. So if you have a function that is continuous on a closed interval, then it has an absolute maximum and an absolute minimum. So if I have a function and it's just a curve, and it goes like that, I can say that definitely there is something going on between them. As long as it's not like a straight line or like a linear function or just a single number like y equals 5, I can say, oh, it's moving around, therefore there's going to be an absolute maximum and an absolute minimum and locals for both of those, whether they be the endpoints or something in between. And now we can start talking about how derivatives are involved with it. Yeah. So the way we do this is we think about what are called critical numbers. Critical numbers are what the name implies. They're numbers that are critical to the function that we can use to kind of discern the properties of a given function. So the critical numbers are classified like this. Critical numbers. Critical numbers are x values where the derivative is equal to 0 or is undefined. So write that down, where d of x equals 0, or is undefined. So, why is this? On a graph, if you think back, when you have a derivative on a curve, the point at which the curve turns around is going to be flat, and the slope of the tangent line is going to be 0. So if you solve the derivative for 0, you're going to end up with the x value where the function turns around. And you can say, I know for sure that that is a maximum or a minimum. And the same goes for, what are they? Undefined numbers. Now, you can't say for sure every single time that these two properties mean that there is an absolute, or no, just any minimum or maximum at that given point. It means there's a possibility of it being there. All you're doing is identifying the locations where there might be a point. So let's say this is x equals, I don't know, 5. When I solve my derivative, I'm going to end up with an x value of 5, but I still have to plug it back into the original function to see whether or not that point is defined or not. So I can say, oh, that's a minimum or a maximum or not, which is one of the two. And yeah, so we can get into some examples soon, but I think that's about it. That's how you use a derivative to find your maximums and your minimums. Yeah, so I'll do some examples in the next video, and yep.